welcome to video 9.2.1. Today we're going to be talking about sigma and pi bonding. So the differences in the double and triple bond and single bond and all of that good stuff. So reviewing, a covalent bond is the sharing of electrons when orbitals overlap. And remember before we talked about hybridized orbitals, we'll be using that extensively in this lesson. So the name for a single bond is a sigma bond. So sigma bond, symbol here, is when overlapping orbitals with electron density localized between the atoms. These are shared. So you have electrons being shared in overlapping orbitals in a sigma bond. And that's your single bond, your very first bond that you're forming. Pi bonds are overlapping orbitals with electron density that's delocalized around atoms. And we'll see what that means in just a moment. So let's take a look at this through an example. So for the following compounds, to determine the number of sigma and pi bonds, draw a representation of how the atoms, about how the atomic and hybrid orbitals overlap to form bonds. So if here we look C2H4, the Lewis structure looks like this. So here we have 1, 2, 3, 4, 5 sigma bonds. That first bond is a sigma bond. And 1 pi bond. The second line on that double bond there is our pi bond. So let's take a look at what this means. So around each carbon, we have a hybridization of sp2. That's because we have a steric number of 3, we have 1 s and 2 p orbitals there, and we also have 1 unhybridized p orbital left over. So let's draw what that would look like. So say we have our carbon right here, and we said we already had sp2 orbitals. So we have 3 of those sp2 orbitals. One's going to be there, one's going to be here, and one will be there. And remember, we talked about what a sigma bond is, and that's what happens when the orbitals are overlapped. So let's look at hydrogen first. So hydrogen only has an s orbital, and so its s orbital is going to overlap carbon's sp2 orbital. So let's just label this. This is sp2. All of these are sp2. And let's look at hydrogen. Hydrogen's s orbital is going to overlap the sp2 of carbon. When it does that, you are forming a sigma bond. So this overlap and these electrons being shared here form a sigma bond. That's a single bond. Okay, the same thing is going to happen down here. And so now we have 2 single bonds, 2 sigma bonds like this. Okay, so now let's take a look at the other carbon. So the other carbon is going to be exactly the same way. So we have a carbon here. Its steric number is also 3, so it's also sp2 hybridized. And now, so it's got 1, 2 sp2 orbitals, and the third one right here, I should have drawn these a little closer, is overlapping. So this bond right here is a sigma bond as well. So let's go ahead and label this. This is a sigma bond, that's a sigma bond, this is a sigma bond as well. Okay, and then the same thing is going to happen over here with our hydrogens. Overlapping. So these are all sigma bonds. Those are all single bonds. Now, the story changes a little bit when we have pi bonds starting to become involved. So in a pi bond, it actually involves unhybridized p orbitals always. So remember we said that carbon right here had a steric number of 3. 1, 2, 3. So it's sp2 hybridized. That means it's using up 1 of its s and 2 of its p orbitals. Well, it still has left over an extra p orbital. So right here, this is the top of my p orbital, and there's the bottom of it. And the story is the same with the other carbon as well. So that's my unhybridized p orbital there. And what actually happens when you have these unhybridized p orbitals is the electrons are delocalized, or they're kind of moving around or associating between these p orbitals. So that's happening both above and below the sigma bond. And we call this, whatever's in purple right here altogether, this is a pi bond. This is not 2 pi bonds. This is 1 single pi bond. A pi bond takes place above and below the sigma bond on both sides of it. So you don't have a triple bond here. This is just a double bond. So this is 1 single pi bond there. Alright, so now let's go ahead and take a look at another example. So here we have C2H2. Now this Lewis structure is a little bit different. So we have actually a triple bond between the carbons here. So here we have 1, 2, 3 sigma bonds and 1, 2 pi bonds. Remember, the first bond in a double or triple bond is always a sigma bond. So let's take a look at what this looks like on an orbital level. So our first carbon is going to be just sp hybridized here, because again our steric number is 2. So one s and one p orbital are combining in steric number 2 to make sp hybridization. And remember, we have 2 sp orbitals and 2 unhybridized p orbitals. So let's take a look at how that's attached to the hydrogen. So there's our sp orbital, and hydrogen, of course, only has an s orbital. So that's overlapping, and this is our sigma bond there. And then let's take a look at the other carbon, where we have the same story happening. So we have, again, our sp and our hydrogen with our s orbital there. So it's not hybridized, there's only one orbital. And then in the middle, of course, we have our sp orbitals overlapping, and this is also a sigma bond. Okay, great. But remember, we also said that we had unhybridized p orbitals. So here's one of the p orbitals, unhybridized. So this, right here and right here, that's going to be one pi bond, and we have a second unhybridized p orbital. You can imagine this coming out of the page at you and behind the page away from you, there and there. These associate as well. So that's your second pi bond. So you have one pi bond, two pi bonds. Remember, the pink, one pi bond, and the purple here, another pi bond. So that's your 2 pi bonds. All right, let's take a look at what happens in a situation where we have more than one possibility. So in this situation, we actually have 3 possible structures, or 3 structures. And we said before that with resonance, you kind of flip between the structures. Well, that's not entirely true. So we're going to take a look now at what's actually happening. So I'd like you to actually pause the video and see if you could figure out what those 3 resonance structures are on your own, and then come back and check your work. Okay, welcome back. So our first structure, and remember to put these in brackets just because we have an ion here, so NO3 minus. So our nitrogen's in the middle, double bonded oxygen with its lone pairs. Oxygen's here and here with their lone pairs, and a negative charge. Now this double bonded oxygen can actually be at any one of these points. So our second option would be maybe a double bonded oxygen there. Don't forget your electrons. And then finally, the last one, let's draw it, it's okay, we'll just take up a little space here, we'll draw kind of small. So we will try to put our oxygen down there as well. Don't forget your electrons. Okay, so we notice that this oxygen that's in the double bond position can be anywhere here. So let's take a look at what this looks like. In all cases, the nitrogen has a steric number of 3, so it's going to be sp2 hybridized. That means that it's going to have 3 hybrid orbitals and 1 unhybridized p orbital. So let's go ahead and draw the central nitrogen. So we have our central nitrogen there, and I'm going to draw one of its sp orbitals here, one of its sp orbitals there, and another sp orbital there. So, sorry, sp2, not sp. So sp2, sp2, and sp2. Now it's bonded to oxygen in all of these cases. So I'm going to go ahead and draw oxygen with its overlapping orbitals as well. So oxygen has a steric number of 3 also. We're only going to look at the oxygen in the case of the double bond first. So it's got a steric number of 3. 1, 2, 3. There's 3 groups attached to it. 1 double bond, 1 pair of electrons there, another pair of electrons there. That means it's also going to be sp2 hybridized. So we have our oxygen with our sp2 overlap there, and we have 2 other sp2s. And in these other sp2s, this is where our lone pairs are hanging out, right? So we're going to have 2 lone pairs in there, like that. Okay, so that's overlapped. We have a sigma bond there. Now we're going to do the same thing with all of the oxygens. Now I'm going to treat all of these oxygens as if they were double bonded, right? So let's say that one more time. I'm going to treat all of the oxygens as if they were all double bonded, and I'll show you why in just a moment. So that means they're all going to be sp2 hybridized. So here, here, another one there, there. Okay. Now let's go ahead and now that we have all of our sigma bonds drawn, so everything's all connected, now let's take a look at where the unhybridized p orbitals are. So oxygen we said was sp2, so it's got an unhybridized p orbital there. That oxygen also does, this oxygen does as well. The central nitrogen is also sp2 hybridized. That means it has an unhybridized p orbital there as well. Now the reason that I wanted you to treat all of these oxygens as double bonded is because they all kind of are. So when we look at resonance, we don't actually have the double bond moving from here to here to here, or we don't have a chance situation in which it's one of those places. In truth, and strangely, it's actually all of the places at once. So those two electrons that are in this pi bond are actually delocalized among the entire structure. So you have the electrons free to go here, to here, to here, to there. So that's where the electrons are hanging out on the top. And the same story is true on the bottom. So I'll try to draw this kind of cleanly so you can see it. Now the electrons aren't hopping through the node there in the middle, but they're hanging out on the top, they're hanging out on the bottom. So this is the real true whole picture of resonance. So again, we don't have a possibility of these three. We don't have this double bonded oxygen moving, switching around places. In fact, they're all acting like they're double bonded, and that pi bond is actually delocalized among the entire molecule. And that's one reason that molecules that exhibit resonance like this are very, very stable. This promotes high stability. So when you have resonance, that's a good thing. That's a stable molecule. And so it's going to be very hard to break apart. Okay, so now let's take a look at the last example we have, C6H6. That is a ring structure. So this is benzene. So I'm just going to kind of draw a line here so we don't get confused with our NO3. So you go ahead and draw it as a ring. Here we go. All right, and it turns out when you draw the Lewis structure, every other bond is a double bond. Draw that a little bit better. That's a double bond. Okay. And we additionally have a hydrogen on each carbon. So as is familiar by now, we can look at the steric number of each of these carbons. Each carbon has a steric number of 1, 2, 3, so each carbon is sp2 hybridized. And of course, we can draw a resonance structure for this benzene. Where the double bonds are in opposite places. So instead of being here, it'll be here. We still have every other one. We still have a hydrogen on every carbon, and every carbon is still sp2 hybridized. Now we know from last time that this really isn't the true picture of resonance. So let's go ahead and draw what that looks like. So I'm going to attempt to draw this benzene molecule kind of just tilted on its side so we can see the top and the bottom of it. So if we look at it, let's see. I'm going to draw it kind of elongated, tilted on its side like this. Kind of attempt to draw it 3D so we can really get a good look. Okay, and I'm not going to draw all of the overlapping sp2 orbitals here because by now we know what that looks like, and I don't want this to look too messy for us. So we know that we have those sp2 hybrid orbitals overlapping everywhere here, and we know that each carbon also has an unhybridized p orbital. And by now, I'm sure that you can see where this is going when we're looking at our resonance picture. So all of the electrons for all of the double bonds are delocalized. They're delocalized among the top p orbitals, and they're delocalized among the bottom p orbitals. And this ring structure is extremely stable due to this. So we have lots of delocalized electrons. They're hanging out in the pi bonds. So again, we don't have one structure or the other. We don't have it flipping back and forth. Instead, we have this structure here, where we have all the electrons that are delocalized among the unhybridized p orbitals forming the pi bonds. Okay, let's take a look at a related topic. So for this example, avobenzone is a key ingredient in sunscreen products. Now for this, I'd like you to just pause, and we're going to do each of this step by step. So draw in the lone pair electrons and the hydrogens. One thing I do need to tell you about structures like this is that in these skeletal structures, wherever you see the angle change like this, there is a carbon right here. So this represents a carbon atom. Even though it's not written, this is kind of shorthand. So this is carbon, this is carbon, this is carbon, this is carbon, this is carbon. This is oxygen because, you know, it's written in right there. But all of these that you can't see any letter for, those are all carbons. So right now, I would like you to please pause the video, and I'd like you to draw in all the lone pairs that are missing and all the hydrogens that are missing as well. All right, welcome back. So let's go ahead and draw in all of our hydrogens. So our carbon has 1, 2, 3 bonds there, so we know there must be another hydrogen there as well. And following that logic through, we can do that with every single carbon. This oxygen right here is missing 2 of its lone pairs, so there. Let's see, what do we have here? Here's a carbon with 1, 2, 3, 4 bonds. Oh, no hydrogens needed there. It's already got 4 bonds, but we do need some lone pair electrons over there to complete that octet. And carbon has 1, 2 bonds. Okay, we're missing 2 hydrogens there. No hydrogens missing here. We have 1 hydrogen missing right here. And typically when you see these structures, you don't actually draw all the hydrogens in. This is just for practice to show us where they all go. Okay, and we have 1 more pair of lone electrons there, and that should be all of the hydrogens and all the electrons. So, part B, determine the hybridization, and the geometry / bond angle at each of the circled atoms. So right here, we're going to look at the steric number, we're going to figure out the bond angle, and the hybridization. So let's do this one together, and then I'll let you work on the rest. So, for oxygen, the steric number is 1, 2, 3, 4. So, steric number 4. We know for steric number 4 we have a tetrahedral structure, and our bond angle is 109.5 degrees, because by now we've memorized that. We also know that this is sp3 hybridized. So 1, 2, 3, 4 steric numbers, sp3. Okay, at this point please pause the video, do the other 3, and then I'll come back and we can check our work. Alright, welcome back. Let's do the next oxygen here. So for this one you should have, that's a steric number of 3, we have a double bond that counts as 1. That is going to be trigonal planar, so 120 degrees, sp2 hybridized. Here, again, same story. Steric number is 3, 120 degree bond angles, and that's sp2 hybridized as well. Finally here we have a steric number of 4, 109.5 degrees, our tetrahedral, and sp3 hybridization. Okay, part C. Highlight the conjugated system in this structure, the system of connected p orbitals. So any conjugated system is a system of connected p orbitals. That means you're going to need to look at where all these double bonds are. So wherever you have double bond, single bond, double bond, single bond, that's a conjugated system. And the reason that this compound actually makes a good sunscreen is because its conjugated system absorbs light in the UV range. So for now, I'd like you to pause the video and highlight the entire conjugated system, or think about it in your head if you don't actually want to commit to highlighting yet. Alright, go ahead and then come back to check your work. Alright, welcome back. So we have this entire ring as a conjugated system right here, because we have single, double, single, double, single, double. And then here as well, if we move over, we have single, double. So that's also part of the conjugated system. Now we don't want to keep going because we have single, okay, there's no double bond right next to it, so we can't highlight that. And then again on the other side we have the same kind of story. So this entire ring, double, single, double, single, double, single. And then from this double bond, single bond over there. And then from single to double bond. Now there is no double bond over here to go to, so that's not part of our conjugated system. Okay, that is the end of video 9.2.1. See you next time for video 9.2.2.